All right, so last time we left off right here. This is the last example in section 2.1. All right, we were solving separable equations. And once again, I was like, this one actually doesn't look quite as separable. I was like, but if we give it a look, okay, so it looks like I can get the t's mostly to one side and the y's mostly to the other. So if I bring the secant over, and I bring the dt over, okay, I got some of it. How do I separate that y and t in the exponent?
Divided. Y of t divided by y of negative, or y of positive t divided by y of t.
Yes. All right. Or right. Remember our rules of exponents. All right. Oopsie. Okay. And so actually 1 over secant cosine. So this actually becomes e to the y, e to the negative t, which is, yes, e to the y divided by e of t, just with some division. So again, always comes back to algebra. Now I can bring that over. So now I'm going to have cosine of y e to the negative y over here dy equals e to the negative t squared plus 1 dt. And then this is a good time, since we just had that example, we're going to integrate both sides, because now I have everything that is completely separable. Over on the left side, what wonderfulness do we see?
Integration by parts.
Yes, but specifically?
Oh, the one where you have to cancel it out.
Yeah, this is circular integration. And then yes, by parts is how you would go about it. All right, that's the circular integration. All right, I love those problems. They keep coming up. All right, on the right side, this is a good time to actually just recall tabular. So tabular, if you recall, you set it up as u dv, and you pick one that's going to derivate very quickly. So let's do t squared plus 1, and one that integrates repeatedly. And then I always, now again, might have a different way. I always start with the positive, because so the first step, right? I take a derivative, I basically derivate this a bunch of times. So let's see, 2t, 0. And then integrate it. And then if you recall, so then, all right, the signs flip back and forth. So you start with positive, and then it goes negative, positive, negative. And it's the same piece of when we set up u dv and then you find du v, right? And you do the same thing with this guy minus the multiplication of these two, but this just sets it up, all right? And I could then write this guy out all the way. So that multiplies, then I say minus, all right? So I follow that sign through. And then I say minus the next multiplication on the next line, which is 2t times e to the negative t. Following that sign through again, plus, because it's taking into account negative times a negative. Basically, that's what the tabular does. And then, 2 times negative e to the negative t minus, and then the next step, which is zeros. On the other side, I did this one for us because it is circular integration. And then, all right, so the tabular integration again, just a little recall of how to do. If you have to do lots of them, I mean, it almost is. It's still faster than doing this twice. Integration by parts twice, but tabular integration speeds things up just a little bit. And then we can simplify this guy down. And then on the right side, plug in our initial condition. All right, bunch of zeros. And here's the big part about this. So once you plug this in, right? Our whole thing with these separable functions is we were finding what other thing after we solved the equation. What were we doing?
Behavior.
Nope. All the other prompts, right? What do they say we're finding?
The interval of validity.
Interval of validity. In order to find the interval of validity, what do we have to do?
Reapply the initial condition.
That's like one of the last steps. What's the first thing we need to do? We need to solve for y explicitly. So how do I solve for y explicitly on this guy?
Not very easily, because you have the sine and cosine functions that make.
Yeah, I got sine and cosine, and I was like I got a y in exponent, aka we cannot. Okay, there are cases, all right, where we can. This one, all right, we cannot solve for y explicitly. Okay. Also, that's why in this prompt,
There isn't there. It's not even there.
it's not there. Okay, and the point is that we have been solving for it, and that's one of the things we want to be able to do, but sometimes you just can't find it. All right, not mathematically, you could find it,
Approximately.
technologically, yes. And basically the point is that here, all right, we left the equation implicitly solved. Because that's what this, the y's are all over the place. So I was like, we can't separate it out and get that nice y equals and then apply those various algebraic techniques we were doing. All right, but finding the interval validity when we can is a big deal. To that end, all right, so this right here is the highest level order of calculus we actually use in this class. Like I said from the beginning, the biggest thing actually we do in why differential equations is like so awesome is that most differential equations are actually solved with algebra, right? We have these crazy derivatives. We solve a lot of equations with algebra, all right? This, though, we can't get away with that. So we have to do a little bit of our Calc 3. All right, exact differential equations. So this is essentially the same process as potential functions, if you recall. All right, we're going to go through it. So I want to solve this differential equation. Notice, all right, can I, is this separable? Can I break them over?
I mean, it could.
No, here's the problem. Okay, also with the dy dx here, right? So I got that guy. If this is being multiplied and an addition, I was like, I can't get them apart with the derivative.
Okay.
That's the big issue. All right, because separable equations always have this form. Okay, this form represented, all right, as basically m plus n dy dx. Once again, this is another one where kind of makes more sense to write it as this. But these are not going to be separable like we just saw, right, in section 2.1. Because these functions have both x's and y's in them, so I can't get the x out across addition, all right, and into the other derivative, basically. So we have a similar equation, all right, similar function that we're used to seeing. Okay. First, I want to suppose, once again, we're going to do this one in reverse so we can see the process. I'm going to pretend, oh, here's the solution. All right, typically represented with
Psi.
thank you. With psi of the equation. Now, be aware, psi is just a means to an end here. Okay? The equation is actually this thing equals a number. All right? So this is really a placeholder because the partial derivative of psi with respect to x is one equation, and with respect to y is the other equation. And that's why this is like potential functions. Because if I take my function psi, now I'm going to do the partial derivative. All right, and I tend to like a Clairaut's notation as opposed to the, the beautiful. I do like those beautiful partial d's too, but okay, so psi with respect to x. So with respect to x, what's the derivative of y squared?
Just y squared.
0.
Okay.
Right? It is now a constant, right? So we've got to remember our partials here. Oh, that's just a constant. That goes away. What about x squared plus 1 times y? Almost.
2xy.
2xy, right?
That one stays.
So, yeah, because that's the constant. And it could be helpful sometimes. Rainbowing that out, x squared y plus y minus 3x cubed. Right, so y squared goes away, that becomes 2xy. Then once again, derivative of y, 0. And then negative 3x cubed.
Negative 9x squared.
Okay, I just want to make sure we're okay. All right, now same thing, partial with respect to y squared, 2y. X squared y.
Squared plus 1.
Oh, yes, you're doing, yeah, I was just, you're absolutely correct. X squared plus 1, and then minus 3x cubed. 0. Now notice, looking back, all right? All right, partial with respect to x. It is exactly that piece. Partial with respect to y. It is exactly this piece. Okay, now be aware, most of our work comes from finding psi. Okay, but I was like, just to see, this is by definition an exact differential equation. Your solution, all right, will have the two pieces incorporated because our favorite little rule, d dx of psi x comma y equals partial of psi of x plus partial psi of y, chain rule, dy dx. What rule is this?
Chain rule?
Well, the chain rule is this piece right here. But I take the derivative with respect to x times, and then technically this would be dx dx, aka 1.
That's what we just did, the mdx plus ndy equals 0.
Yeah, this is exactly that definition. But what's this rule called, right? First derivative second plus second derivative first. That's basically what that became.
The product rule?
Yeah, it's the product rule again. All right, it's still just the product rule. All right, and then yes, Josh, you're absolutely correct. This then is the definition, all right, of all right what with our chain rule, all right, we have our chain out there results because of the product rule. And then just as a note, as usual, with a derivative, what's our favorite value to set it equal to?
Oh.
And since this is equivalent to basically doing the product rule, that is sine of x comma y derivative equals 0. When I have something like this is exactly what we did with linear differential equations. What did we like to do? If you have something derivative, integrate both sides. And again, this is proof, right? All we're doing here is just basically the proof of this. We integrate both sides. What's the integral of 0? C. Constant. And so the point is that my point is that psi is just a means to an end, because we actually end up with our solution of differential equation equal to C. But a lot of times when we're going through this, okay, I'm saying psi equals this thing, right? And it's really psi equals C, all right? So the psi, it's not like f of x, okay? It's not f of x equals this, all right? Or y equals like we were doing before. This is the function equal to C, because notice I have x's and y's in the equation. All of that boils down, okay, Two, all right, our differential equation, all right, for exact tests. So the first thing we're gonna do, as everything with differential equations, make sure we're in the right form. Okay, in either of these forms, perfectly fine. Okay, then we test, all right, and a lot of times you can kind of see it, right? Everything is all implicit, it's all together. All right, we've got x's and y's next to each other, two t's, whatever variable. We want to test to make sure it is an exact differential equation. Then we're going to go through the process of solving for psi. All right, so back to our example, we already know our solution here, okay? We identified, so we have our equation, and again, I really like the form 2xy minus x plus. And the reason I like this form is this. Basically, one is m and one is n, okay? That part isn't nearly as important as, so if I call the first one m, and the second one, right, is n. With this form, what I like about this is this says this was the derivative with respect to x, which means if I want to test to see if these are exact, then I do the derivative of the opposite of whatever this is. So that's the x, so I need a partial with respect to y here. And that's kind of why I like that form a little better, because it's telling me, oh, just do the other. So partial with respect to y, so 2xy.
2x.
2x. And again, we got to jump back and forth. And then negative 9x squared.
0.
Oh, that was nice. So same thing for the other one. And x, partial with respect to x. So 2y.
0.
X squared.
X.
1. Oh,
They're the same.
they're the same. Wow. Since partial with respect to y equals partial with respect to x. And that's the test for exactness. Okay, now we get to do the hard part. I was like, so making sure, all right, they are exact, then we can go back and solve this. And we're going to look at a case too where they don't end up exact, and we'll have to do that. So, all right, if I have nx and ny, all right, in order to get, right, from our equation back to, or to our psi, what do you think we need to do? We have a bunch of partials everywhere.
Try to integrate them.
Yeah, we need to integrate. So really look at m, look at n, and basically pick whichever one is easier. Now in this case, is one easier than the other to integrate?
I don't think so.
No, like they're the same. But if one was e cosine and one is x squared, right, then you would. All right, so I picked, because it doesn't matter. I picked m. So integrate either m or n. And basically, I'm doing this piece, all right? I'm doing just this piece. The integration is already there, right? And it's even telling us which one we're doing. So they're both the same in this case. And our whole goal, again, we're trying to find psi. So I picked m dx. Now here's the big part. So I picked M, right? Integrate x with respect to x squared y minus 3x cubed plus what?
CX,
Yes. All right. Not x though, but
C1 or like what would you denounce it? Just annual C.
well, a function. I called it h. H
Of X.
almost. Why? Because we got the x's out of there, right? We integrated the x's out. All right. So there's just something that has to be a function of y. All right. So it's still this isn't just a constant because this could be
A function.
y squared, y cubed, whatever, root y. All right. So there's something with y left, right? So this is the potential function part. Once you have that, all right, then, all right, we want to line it up, take the derivative. Take the derivative with respect to that variable. So now I have psi of y. So let's see, x squared, that goes, right, the negative 3x cubed goes away. And then what's the derivative of h of y?
Just dy over dx.
H or H prime Y.
H prime y. So again, we just got to keep track of, we're doing derivatives and integrals. So then we take that and we need to set whatever the partial we did, we set equal to the other function. In this case, whichever one you didn't select, n. Right? So we identified n, right? 2y plus x squared 1. Then we just fill in the missing pieces. Oh, look. Is there an x squared in both of them? Yep.
So we know our derivative of that function.
And then what we actually need, right? We don't need h prime of y. We actually need h of y. So h of y equals the integral of h prime of y. D what? Dx?
Dy.
Oh, dy! Because we already did dx, and basically you have to do dx and dy. That's why it doesn't really matter what you start with, all right? You start with one because you're going to have to do the other, but you want to start with the easiest one. So y squared plus y plus c. Ah, we are to c now. Okay. So putting it all together, we end up with psi equals x squared y minus 3x cubed. Those are the pieces we got from above. Then h of y, right, plus c. Now, here's the weird thing. Once again, psi is a means to an end. So it's not actually plus c. This whole thing equals c. So the solution the equation actually is this, all right? Not the solution to the d. So the solution of the d is actually this. Then our very last step, we had an initial condition, all right, y of 0 equals -3. But that's the heavy lifting, basically. And so, yeah, unlike our others where we actually got x equals y equals okay, these are almost always explicit. And again, psi is a means to an end. So be aware that last plus c we put on it isn't even really necessary. Because even though, right, we're just for completion of integration, we were like y squared plus y, oh, plus c. So we're down to the variable. But it's not important because actually the whole thing equals c because psi is representing the variable piece of the equation. All right, let's do another one of those. And this time, I also want to find the interval of validity at the end. So solve the following IVP. All right, form is everything. So what's going on here? And what might, these ones, I love prime notation, but when I see something that looks like it might be exact, dy dx is kind of my go-to. And what else do I need to do maybe besides that for the proper form?
Add the dx dy.
Yes. Yeah. But notice the equality for the proper form of this guy. What's the equation equal to?
Oh,
0. Okay. So these ones, everything is all on one side. So yes, because since this is dy dx, that actually makes this dx minus 2, 3 minus x squared y dy equals 0. Form is everything. Once I'm there, so once again, m equals 2xy squared 4 n. I better bring that through raise. Let's see, negative x squared y minus 6.
Two X squared Y.
No, two x. Trying to do these steps. All right, two x squared y. And then, once I have that, test for exactness. And y and x. And oh look, 4xy, 4xy. Uh, if it doesn't, and we would have seen it in just a minute, right? If I left that two off, I was like, it would have been like, oh, I would have got 2xy, 4xy. Oh, double check to make sure it's exact. Because always make sure that we're going to see a case next that when it's not exact, and it adds quite a bit. So I definitely want it to be exact. Okay. So I would definitely double check my math before I continue to proceed, because the alternative to not exact equations is unfortunate. Once again, all right, then our case, whatever we want to pick, now we can start finding psi, and it doesn't matter which one, pick them again, because it's all the same. They're both equivalent in difficulty. Do the integral to find psi, then take a partial with respect, all right, to whichever variable opposite you integrated. So again, this is all opposites back and forth. Oh, I have dx, then I do derivative y, and then do dy, and then do dy. Then set that this guy equal to n, and again, these should always line up pretty closely. And oh look, that one actually lines up really well, indicating h prime of y equals -6. That one barely needs an integral to solve. And then again, I can add the plus c on there. It doesn't really do a lot, because just for the completionist part of you, maybe, when you write psi of y all the way out, you can attach that, but in the literal next step, I'm going to actually say, right, so the solution. Because it's always equal, right? The differential equation is equal to the constant. All right, plug in our initial condition, all right, to find our value C. Gives us our differential equation equals this guy. All right. Now this problem, unlike the previous one, this said find the interval of validity. Once again, in order to find the interval of validity, what do we have to do?
Solve for y.
Solve explicitly. This is going to be easier than the one with sines and cosines and exponents. Okay, this is still not my favorite solve for y. The point is that this one, all right, the only way to actually do this is by, we're essentially doing quadratic formula. A is x squared. B, all right, is -6. And C is the last piece, 4x minus 12. I brought that over. I can then solve this down, and notice I just wrote this out for us. Okay, so this is in the lecture notes. Okay, because I was like, oh, we get this, and I get a bunch of x's inside there. I simplify this thing down. Okay, then we know with discriminants, it's got to be greater than or equal to 0. So I have now this thing greater than or equal to 0, which is a cubic. I then graphed it. Okay, and if you want to verify this, here's the window I used. Okay, so there's the window, which yields -infinity to 3.22. Okay, applying then, right, as we do, applying the initial condition of x equals 0. Which of the two is the valid one? Or sorry, x cannot be 0, right? Because I have x in the denominator of my equation. X can't be 0, so it breaks it into 2. Then I apply my initial condition, which was -1. Which of the two is the valid interval?
The first one.
Yep. Oh, it's right here. So because I apply -1, I don't look. Not really so my point is this. If we can't solve it explicitly, can we solve, like, if I can't, solve it algebraically explicitly, can I still find the interval of validity?
In theory, because they approximate an issue.
Oh, this is it. I found it.
So you couldn't solve it explicitly.
I was like, solve it in our standard sense.
Okay.
I was like, I'm technically solving this function. By definition, quad form says I'm solving it explicitly, but I wasn't able to write it out nicely. Y equals, right? I had to use quad form. Okay. And my point is it still possible? Yeah. Does it suck a lot? Yeah. Okay. So one more note. If I say find the interval of validity, you should be able to find it. Okay.
You're not gonna do as dirty and.
Yeah, I'm not gonna give you something like this, like on the test. I can burn through these in the home fund.
Sure.
Like I was like, but on the test, this just takes way too long because I was like, I got plugs in, I'm simplifying this down, I'm doing plus and minus, discriminant. Like it's like I'm remembering all my rules of algebra to solve this.
would you ask us to find the interval of validity if something did not truly have an interval of validity?
No, absolutely not.
Okay.
No, no.
I try to trick us like, oh, you should have been able to recognize
That's
that.
actually, we're gonna talk about that next class probably. And there's a couple of theorems that define intervals of validity and the uniqueness and existence basically of differential equations. It's actually really good. All right, so we're gonna talk about that and unique, because existence, everything we're gonna be doing, they exist. All right, and then uniqueness is usually defined by the IVP, the initial condition. All right. All right. Last other little piece here with exact differential equations. So with an integrating factor, I can convert a non-exact differential equation into an exact differential equation. There is no fast way around this. If you we identify our form, we do our test for exactness, we identify it is not exact, so exactly right. So when I left the two off, I would have been like, oh wait, this isn't exact, double check. Then you create the integrating factor, okay? The integrating factor, now notice, right, d mu, dx, and with the mu, we got this over here, so do the same thing, we identify it, and then I have to solve to find what that is, all right, to put it into the equation. Be aware, here's another question. This is not on the quiz, because if I say solve the differential equation and the test fails exactness, double check. Because this adds a ton of work. I do have some of these in the home fund, and they just get long very quick. All right, so, all right, we have our form, and it's actually in the correct form, not my favorite. Let's just rewrite it because I like my favorite form. On a totally other note, the signs are important, right? This is exactly what we were talking about with our linear differential equations that we're doing, right? It's always a plus, and then you integrate the integral of PT because that's a plus, right? Just like the opposite of what your book was saying. Okay, so same thing. This has to be a plus, all right? And that's why I want you guys to be able to recognize that, oh, you had minuses there and you guys ignored those signs, okay? So I was like, the forms are important, all right? And most of the ones I do, I always try to make a positive. I was like, we'll indicate very heavily if it's negative. But the forms always being positive means that if you have the opposite sign in there, that changes the whole problem. Okay, so once in there, all right, so this guy, M. So M equals 3xy plus y squared. N equals x squared plus xy. So that's dx, which means one's dy. And that's why I just love it, because it's always just opposite. That's why I like that form the best. All right, so with respect to y, 3xy plus y squared, what does this become?
3x plus 2y.
With respect to x squared plus xy.
You get 2x plus y.
Are these the same? No. And I think that's enough where I didn't write them down wrong or I didn't mess up. Okay. Not exact. But they kind of seem close, right? I mean, definitely feels like it's close. Okay, so the integrating factor. The good news is we already found the pieces associated. Okay, so just simplifying the numerator down. Now what should we do? And here's the big, here, notice that, right? I have d mu dx and a mu. So notice, yes, I'm gonna have to do that eventually. But just notice that in order to, the integrating factor here is not nearly as nice as mu equals e to the integral of pt. Okay, so you have to mess with this each time. And yes, absolutely, I want to get that over here and over here eventually. But let's simplify a little bit first. What else should I do?
You can pull X out the bottom.
Haha, don't forget our simple algebra. Oh, already that brings me joy because what?
You get the factor that can cancel.
Yeah, I can cancel that. And then now I have something that actually doesn't look nearly as horrible. But you have to mess with it and pay attention. And then now I have this, right? I have mu over x, d mu dx equals mu x. And then absolutely, this is by definition a separable differential equation. Bring the mu's over, bring the x's over. And I'll look. Okay, let's integrate both sides. And actually, it turns out to be not so bad. Now, beware, just like we did with linear differential equations, what did I kind of leave off after I integrated?
Or C.
C, because it's an integrating factor. Am I going to get a C somewhere?
It's gonna cancel out one.
Well, I'm going to get it later. I don't need it in the integrating factor.
Yeah.
That was because remember we did that whole, that's why I did that proof, because a lot of this comes back to linear differential equations. Then I don't need the C in my integrating factor, so I'm going to get an integral when I actually do my differential later, because this is going to go back to doing size, right? So we know that whole equation is equal to C, so I got that covered. And then if I have ln of mu, ln of x, this actually becomes
Like mu equals X.
yeah, mu equals x, right? Like it's just raise both sides to the e, cancel the ln's, whatever you want to say. Mu equals x. Actually, not the worst integrating factor we've ever seen. Once again, with integrating factors, what do you do with them? So now I found that.
You gotta go E
Multiply
to
it.
the,
Multiply it by. No, it's not.
okay, so that thing is,
That's only for linear.
okay,
Linear. This is a different one. So, but by definition, an integrating factor is just something you multiply
by through.
with. When you have a linear first order differential equation, it's e to the
Solution, okay.
integral pt.
Okay.
And I base a lot of the analogies on that because that's the most famous integrating factor equation. But you can do this for everyone. But the point is once you find it, multiply back into. Now okay, once I've multiplied it through, I still have it in, it's still in the correct form. We go through my equals nx equals, when I now take the partial with respect to y of this guy, 3x squared plus 2xy, 3x squared plus 2xy. Now
Again.
this is an exact t. We did all that. Now what do we need to do?
Solid.
Yeah, I was like, that's why this is just the, oh, we found the integrating factor to do the test, and then we tested it and found it's exact. Now we actually have to go back through and actually solve the whole thing.
Is there a scenario by which we do this integration factor and it would still be?
It still wouldn't work. Only if it would, the issue would be right here. If you get here and you couldn't integrate this.
Okay.
Because it's possible. Is there stuff we can't integrate? Yeah. So it's possible I could get an equation that I could not take an integral of.
Okay.
Okay. So you would
At that
be
point.
stopped right here.
Okay.
So yeah, there's no way you found the integrating factor, you multiplied it, and you were like, wait, it didn't work. I was like, you would be stopped right here.
Okay.
So that's at least good to know that you're not
Able to get stopped somewhere.
Yes, you're able to get stopped. You're not way deep into the problem. Okay. So, all right, let's see. Oh, let's use n this time. Just to mix them up. Now, once again, are these the same difficulty of integration? Yes. Now we take the partial, since I used n, doing everything in reverse, take the partial with respect to x of the function. Same thing, all right, call it g of x, still call it f of x, h of x, it's all the same, right? G of x, all right, then derivative with respect to x is g prime of x. Set this guy equal to then the other one, m. Sine x equal to m now. And this is when you really know you're on the right track. Why do I think I'm on the right track?
Yeah, the same.
Well, almost. What's missing?
The H of prime of y.
What G? We're calling it G. You call it H. It doesn't matter. So G prime of x equals
It should be a constant or a zero.
0. Well, but you already skipped ahead. What's G of x?
It should be a constant.
Constant. Yeah. So I really know that like this part is really easy because since G prime of x equals 0, then G of x equals C. Oh, look at that. I was like, I don't even really need to do the integral on that one. Pretty sure I got that one. So again, now I tend to write this part out. Psi equals, again, psi is mean to an end. Just write it out to just keep track of what we did. But a lot of people skip this step. Because the actual solution it's the same thing, but actually, right, it's equal to C. This is the actual solution. Psi is a means to an end, all right? We write it a bunch, all right, as we're proceeding through, just to make sure we're keeping track of all our pieces, all right? But it is just a means to an end in the actual equation. And then last thing, apply the IVP, apply the initial condition.
We didn't have one.
Oh, we didn't have one. Oh, paying attention. Good. All right. There was no initial condition. All right. So that is just the general solution. All right. I want to talk about Bernoulli a little bit, maybe just do one, start the example here. So Bernoulli, all right. One of my favorite people because Bernoulli was a what?
Physicist?
No.
Was he a mathematician, really?
He's a mathematician. All right.
Fluids is the deal.
I mean, at that point, I don't think they had nearly, they were always mathematician, physicist, scientist. So yes, I was like, Bernoulli has a lot of credits, all right, but actually one of the other ones is the Bernoulli equation in statistics, one of his credits. So, all right, and it's really all about Bernoulli's zeros and ones, right? Boolean, Bernoulli. I was like, so many of them, right? They were all about zeros and ones. His equation, oh, that actually reminds me. The exact differential equations we just did. Is this a linear or nonlinear differential equation?
It's non-linear because of the square term.
It's the y squared, okay? What about this one?
I think that one's linear.
Linear. So notice that exact can be applied to linear or nonlinear. Bernoulli differential equations are almost explicitly nonlinear. They all have, I mean, it's possible that that could be a one, but they all have, all right, y to some power, negative, positive, doesn't matter. But as soon as y is raised to an exponent other than one, all right, it becomes nonlinear.
Or zero.
Oh, is that?
Well, technically, y to the zero would make it linear. So
automatically, right?
yeah, because y to the zero is just one.
Yes.
So, but yes, it could be raised to zero. It could be raised to negatives. A lot of times they're raised to zero.
Squared terms or
Integers, yes.
1/2, 1/4.
Yes.
2.
Could be fractions. I was like, this approach works for everything. With these, as with everything, form is going to be crucial. All right. The form that we are going to be looking for, all right, regardless of where it begins, okay, we're actually going to have something next to the differential now. All right. And then the other power, all right, is here. On the right side, we want a function with just a bunch of x's, okay? So this kind of looks like our linear differential equations, but this time we have some nonlinear power of y. The process actually is going to be really, really easy on us. We're going to identify a substitution, and then we're going to take a derivative, and we're going to have to do chain rule. And identify, and most likely, I think we're going to see that we once again, it's going to possibly look something maybe like a product rule in there, or at least one substitution of another. All right. We're going to be able to reduce it down to our favorite first order linear differential equation. So we're going to do a little substitution. All right. and then be able to, this is all printed in the notes. You don't have to write this down, Lane. I mean, I'm just saying, you look like you're panic writing. If this is just given to you, that way we can just talk about it, you don't have to be like, oh my God. It's like,
It's easy to do.
yeah, I was like,
Same boat here.
if it's up here, like, if I'm not writing it, then I just gave it to you, just like, that way you don't have to like write it out. Okay, so, all right, we're gonna identify and then we're gonna get this, we're gonna do a little substitution. Once we're in the right form, we do a substitution, make sure that everything plugs back in appropriately, and we should end up with a first order linear differential equation that then we could solve with what favorite technique?
First one we use.
Yeah, which was called what?
The integrating factor.
Integrating factor, yeah. I was like, integrating factor technique. It's such a common technique. So let's just look at one of these. Okay, so form first, foremost, always. The form means I need the X stuff over here. So I'm going to divide this whole thing by Y squared. And for all right, so then everything's about the substitution. And, all right, V, U. I was like, picked V, but of course you can pick U. All right, if I pick one of these, all right, let's be clear here. This is actually a case with all ones and negatives running around. Let's make sure that we got that Y prime or even dy dx here, just to make sure our notation doesn't blend together, that I have -1, -2, and a Y prime, right? Careful with your notation. So I want to pick a substitution and I'm going to take a derivative of it. So I really only have two options. I have y to the -1 and I have y to the -2, okay? So I want to pick one of those. Which is the derivative of which?
-2 is derivative of -1.
So let's pick this guy.
-2.
No, the -1,
Oh, okay.
because dv, or v prime, equals -1, y to the -2, and then chain rule, what's the derivative of y?
Y prime.
Y prime. Okay, so this is where the notation can get a little, like, because we have, by definition, Bernoulli has exponent stuff, okay? So definitely make sure that your primes aren't becoming ones and vice versa, all right? So you want to make sure you're just paying attention. I was like,
Well, for me, the Y to the N looks like a double prime. You know, it's like it's a visual thing. We doing Y to the N when we were doing the first Bernoulli.
At the very top, it looks like a double.
It looks like a double.
oh, up here?
Yeah, that Y.
Yeah. Yeah,
That
this
looks-
guy,
yes, sir.
yes, same. So, it depends, like, I mean, we of course can always write dy dx. And some people do prefer it. Like, it's all about just keeping track for yourself. Whatever is most helpful to you, that's what, I mean, I always write capitals, you know, I have to be able to read my own handwriting and know what I'm doing, because if I screwed myself, that's the worst like feeling I have. So yes, you want to convert everything dy dx. I was like, the prime notation can be really nice, but it just blends fast. I mean, even these, like the little font italics sometimes look like ones. So again, yes, whatever is helpful, and just pay attention for yourself. Okay, so I have this. Notice right here. Okay, so I already see good news. Okay, so I let v be y to the -1, so this guy's going to become v. Okay, we're not messing with the x's at all. All right, over here, that actually lines up pretty well. What do I need to fix here?
The negative.
That's a pretty simple fix as well. negative v prime equals y to the negative 2 y prime. Now I can put both of these pieces back into my equation. And when I did have powers, all right, I had I had a nonlinear equation. Now we have to turn this into a linear. This is now a first order linear differential equation. The last step, all right, since we now have V's and we're going to get this and we're going to solve this down for V's, we'll have to do one last step, which is to convert it back to Y's. All right, so it kind of adds a step at the beginning, but the actual solving of this, now this is something, right, that, I mean, this is why we did like, I don't know, it was like 10 examples of linear first order differential equations, right? Because this just becomes so important. One more time, let's just review this. What's the correct form?
Where you at, like for Bernoulli or for the?
This is no longer Bernoulli.
Yeah, it's now true in the linear, whatever.
Yeah. So what's the correct form? And actually, I shouldn't ask you, Zach, or Josh, because
I know, it's plus, plus. Plus, but we have minus there.
Positive, yeah. So I was like, I need to make sure that I change that. It's got to be a positive in front, v prime, all right? And then I can actually write this as plus negative 4 over x, v equals negative q. And then I can identify, right, integrating factor with the integral p t dt. And again, the important part of that negative just has to come with me. Integral negative 4 ln of x. But that just becomes x to the negative 4th. Multiply it into my equation. Multiplied in, what do we see? Product rule, right? And this one does line up. So even though there's a negative there, right? Because the negative of x to the negative 4th comes down and becomes negative. So again, just always want to make sure we're double checking our signs. So x to the negative 4th v product equals negative x to the negative 1. Integrate both sides with respect to dx. Gets us ln of x, solve this guy for v. So, well, other these are correct. All right, and then the last and important step. We need y. So
You just plug this back into our
v equaled,
1/y.
yep, 1/y, y to the -1. Which means that now we have y to the -1. Y is going to be a long right here, you're correct. 1/y equals x to the 4th c minus ln of x. To then solve this, y of x inverse
Yeah, that's a quick question.
yes.
How can you never put absolute values around the natural logs?
Because almost in all cases, I was like, we end up with like positives or something, and truly it's because I don't care. I was like, it's like this excessive thing of like, oh, it has to always be positive. Yes, I was like, anyone past like high school level algebra knows like the restrictions on absolute value. So, yes,
I was just curious
for full definition.
if you would knock us a point, or if you're okay with that
No,
notation.
I was like, because way too often, even when we get to the problems, we assume, oh, it's like positives in this case or that case. And we have imaginaries to deal with the rest of it. So I'm always like,
Whatever.
yeah, whatever.
Okay.
Like, okay. All right. So, but basically same thing, linear first order differential equations. I was like, the Bernoulli turns into the same thing we're very familiar with just it's just a step at the beginning, step at the end. Okay. But in order to, just like with everything, in order to identify that substitution, you got to get Bernoulli in the correct form to find the substitution.